Let's take a look at resonance in open pipes. This worksheet comes to us from the physics classroom, so be sure to check out these resources above if you have additional questions or want to look for some extra practice. When looking at open pipes, you have ends on each side where air is free to move with maximum displacement. That means you're always going to have an antinode at each end, a place where the wave is going to appear sort of open to you. Then places in between where the air is not moving at all, the antinodes. Let's take a look at what these standing waves actually look like. The first harmonic, shown here, is the lowest frequency an object will resonate at. It's also sometimes called its fundamental frequency, as referenced above. The first harmonic contains a single node of minimum displacement, as well as antinodes at both ends. So I'm just going to put a dot here in the center to remind me where one of my nodes should be, in this case my only node. I'm going to have antinodes at each end, so the way this is going to have to look is something like this. That's the first harmonic. The second harmonic has two nodes and still antinodes at each end, and so it looks something like this. And I've gone ahead and drawn in the third, fourth, and fifth harmonics as well. You can see at the third harmonic there are 3 nodes, the fourth harmonic there are 4 nodes, and the fifth there are 5 nodes. What's really important to recognize then is how the harmonic level affects the wavelength of each of these waves, because that in turn determines the frequency. The length of this pipe determines what sorts of notes we can play here. So if you look at this first harmonic, this wave shown here, it starts at a crest and it ends over here at a trough. So what you're looking at, the length of this pipe represents only 1/2 of a wavelength. This length is equal to 1/2 of this object's wavelength. So in turn also we can say the wavelength is 2 times the length of this pipe. So if you have a pipe here that's say 0.7 meters long, the wavelength is going to be 1.4 meters. When you advance to the second harmonic, you have a crest at the start here and a crest at the end here. This is one complete wavelength. So it's 1 wavelength equals the length of that pipe. When you get to the third harmonic, you now have 1.5, or I'm going to write this as 3/2 of a wavelength, which means the wavelength is equal to 2/3 the length of the pipe. When you get to the fourth harmonic, you have 2 complete waves, which means the wavelength is equal to half the length of the pipe. And when you get to the fifth harmonic, you're looking at 2.5 waves, which I'm going to write as 5/2. The wavelength then is 2/5 the length of the pipe. In fact, as you increase the harmonic, you go from 1/2 to 2/2 to 3/2 to 4/2 to 5/2. There's a regular increase from one harmonic to the next. So we can use that regular increase to make some fairly simple calculations progressing from one harmonic to the next. For example, in this problem here, we're told that the first harmonic frequency is 384 hertz, and we're looking to figure out what the third harmonic frequency is. Because going from first to third cuts the wavelength by a factor of 3, when we go up to the third harmonic, we're going to have 3 times the frequency. So we just multiply 384 times 3, and we get a third harmonic of 1152 hertz. For part B, we have to do something similar, but just in reverse. We're told the fourth harmonic frequency is 1296, and we're looking for the first one. The first one has to be 1/4 as much as the fourth one. So if you take 1296 and divide it by 4, you get 324 for your fundamental or first harmonic. Letter C is just slightly more complicated. You've got a fourth harmonic frequency of 528, and you're trying to figure out what the third is. Maybe the easiest way to think about this is to take your fourth harmonic frequency of 528 Hertz and dividing that by 4 just to get back into your fundamental or first harmonic, which works out to 132 in this case. And then you can just multiply that by 3 to figure out what your third harmonic would be, in this case 396 Hertz. I've gone ahead and transferred the relationships of wavelength and length from the previous page for each of these particular standing waves. This is a third harmonic wave, a fourth harmonic wave, and then indicated here, of course, first and fifth harmonic. So I'm just going to plug numbers into these equations to get my results. The wavelength in part A is equal to 2/3 the length. The length is 63 centimeters. I multiply that by 2/3 and I get 42 centimeters for a wavelength here. Similarly with part B, if it's an 85 centimeter air column, the wavelength is half of that length. You have 42.5 centimeters for the wavelength in part B. Part C, the wavelength is twice the length at first harmonic, so I've got to take 42.5 and multiply it by 2, which should give me 85 based on what we just did in part B. And then for part D, the 1.4 meter long air column represents a 2/5 length to wavelength conversion. So multiply that by 2/5 and you get a wavelength that's equal to 0.56 meters or 56 centimeters. For the last few math problems, we're focusing primarily on this equation. The frequency of a wave is equal to the velocity divided by 2 times the length, where this n value represents the number of the harmonic. There are other ways to approach solving these problems, but getting accustomed to that equation is probably going to be your best approach on this particular sheet. So you see the answers below. I'm going to show you how they're worked out. It'll hopefully save us a little bit of time as I just give you some of the broad strokes here. For number 7, you're told that there's a second harmonic frequency of 882 Hertz, and you're given the speed of the sound through the air at 345, and you're asked to figure out the frequency of the first harmonic and the length of the pipe. So the frequency of the first harmonic is really just half of 882, because the second harmonic should be twice as high a frequency as the first harmonic. So start by taking your 882 and dividing it in half to get your 441 Hertz first harmonic. And then solving for frequency and length is using this equation here. So if the frequency of 441 Hertz is equal to the number of the harmonic, which in this case is 1, times the velocity, which was given to us as 345, divided by 2 times the length. So we need to do a little algebra here. You can cross multiply if you want, or you can multiply both sides by 2L. Divide both sides by 441. And what you get is what boils down to this. 345 divided by 441 is equal to 2 times the length. So we have to divide again by 2 to get to our length, and that should work you out to the number I have here of 0.391 meters. On the next problem, we're told the first harmonic is 196 Hertz, so we're given initially a frequency, and told the length of the column is 89.2 centimeters. It would be a good idea to just make a note of those variables. Frequency, 196 Hertz. The length of the air column is 89.2 centimeters, but we're not going to leave it like that. We're going to convert that into meters, 0.892 meters. And we're asked to figure out the speed of the wave, the velocity. So if we go back to our equation, frequency 196 equals n, which is 1 for the first harmonic, times v, which is the variable we're solving for, divided by 2 times the length of our flute, 0.892 meters. So we're going to multiply by the bottom of our fraction here times our 196. We'll divide by 1 if you want to, but you don't really need to, of course. You should end up with a velocity here of 349.7 meters per second. For number 9, you're asked to figure out again the length of the flute. So the length is our unknown variable. We're given a velocity, which is still 345 meters per second. We're told frequency 262 hertz, which we're going to go ahead and treat as the fundamental or first harmonic, and solve using that same equation one more time. So 262 hertz equals n, which is just 1, times 345 divided by 2 times the length. And just like we did up here with number 7, you're solving for length and should get 0.658 meters as an answer here. And lastly, for number 10, you're asked to figure out the frequency of the 63.8 centimeter long open-end air column shown to the right here. You're given again the speed, we're given the length here, which we are going to convert to 0.638 meters since our velocity is in meters per second. And then we just have to take a quick look at our diagram to see what kind of harmonic we're working with here. To find the level of harmonic when you're looking at a picture, just count the nodes. There are 3 nodes here. That means we're dealing with the third harmonic, which means when we get into our equation that says the frequency is NV over 2L. This is the first example on this page where n is not going to be 1. It's going to be 3 to represent the fact that we have a third harmonic here. So the frequency is equal to 3 times the velocity, 345, divided by 2 times the length, 0.638. No algebra here, just crunch out those numbers and hopefully you'll get something like 811 hertz for that one.